Hi, welcome back to Introductory Statistic. This week we're going to talk about the tests of significance. We'll cover chapter 26 of our textbook. So we want to know in this section whether something is due to chance or something else. So there's a test called the tests of significance that allows us to answer this. And it's possible to nowadays read a research article without running across tests like these. So it's important to know what they mean. So suppose you have a box of ticket, and we have two investigators who are gonna look at this box and try to understand what is in this box. And Dr. No is gonna say that the average is 50, and Dr. Alternative thinks that the average is different than 50. So they're gonna do a test to kind of determine who's right. And so they agree to take a sample. They pick 500 tickets at random, and because the box is big, we're gonna say that the difference between picking with or without replacement is small. And so let's say the average of the sample turned out to be 48, and the spread, the SD of the sample, is 15.3. So Dr. Alternative is going to say, well, 48 is different than 50, so he argued that he's right. Dr. No says, well, 48 is so close to 50, it's only 2 away, so that's just due to chance. And so he thinks he's right. So we want to know whether 48 what does 48 say something about the average of the box, and whether the difference is big enough to say that maybe the average is not 50. And so we want to see whether 48 would just happen to be by chance. And so the SE will help us determine that. So the SE, the formula is root of the number of draws times SE of the box. Because we don't have the SD of the box, it's unknown. We're going to use the bootstrap method that we talked about to use the SD of the sample, 15.3. So using that, we find the SE of the sum is 342. And now we'll try and find the SE of the average. So we divide that by 500 to get 0.7. So this says that the 48 is actually 3 SE from 50. And again, the way we see that is 48 minus 50 is -2, divide by 0.7, is about -3. So that means that 48 is -3 away from 50, and that's very far away. When we talked about the normal distribution, we saw that the area between two standard error to the left and 2 to the right, that area was 95%. And the fact that this is even further away, is outside that region, says that it's very unlikely to get something this big. And so because that difference is so big, we conclude that the average of the box probably isn't 50 and is some other number. Because the expected value of the average should be 50. We should get the average 50 if the average was truly 50 from our sample, but the fact that we get something so small means that this is unlikely that the average of the box was 50. So here's the issue. We think that one side of the argument thinks that the difference is real, the other side thinks that it's just due to chance. And so this test of significance allows us to kind of fend off the attack that is only due to chance. Well, this argument, we'll kind of argue against the fact that it's just due to chance. So if the observed value is too many SE away from the expected value, that's hard to explain by chance. So we're going to learn about a few different words: null hypothesis, alternative hypothesis, test statistics, and p-value. And these words are very important in this discussion. And so in the last example, we take a sample of 500 tickets, and we saw the average of 48. And 48 was the observed value. And the argument was about the interpretation. What does the sample tell us about the other tickets in the box? So Dr. No thinks that the observed difference is real. There's a big enough difference. But Dr. Alternative thinks that the difference is real. Dr. No thinks that the average of, was 50, but 48 was just due to chance that you get 48. So the null hypothesis and the alternative hypothesis are two statements about the box, not about the sample, and each hypothesis represents one side of the argument. The null hypothesis says that the average is 50, The alternative hypothesis says the average is less than 50. So Dr. No is defending the no hypothesis. According to him, the average of the box was 50, and the average turned out to be lower than 50. It's just due to chance. It's just the luck of the draw. Dr. Alternative thinks that the average is lower than 50, and her argument is this: the sample average is so many SE below 50 that Dr. No should be wrong, she thinks. So the no hypothesis corresponds to the idea that the observed difference is due to chance, and so to make a test for significance, the no hypothesis has to be set up as the box model for the data. So we basically assume that the no hypothesis is correct. The alternative hypothesis is another statement about the box. It corresponds to the idea that the observed difference is real. So in the previous example, Dr. Alternative temporarily assumed that the no hypothesis is correct. The average is 50. And on this basis, she calculated how many SE away from the observed value of the sample average was from the expected value. In other words, 40 minus 50 divided by 0.7. So 48 is the observed value, 50 is the expected value, 0.7 was the SE. So doing this gives us a negative 3. This says that 48 is 3 SE away from 50 to the left. And so this number is called a test statistic. A test statistic is used to measure the difference between the data and what is expected on the no hypothesis. And Dr. Alternative test statistic is also called the z-test because it's using the z-score that we saw earlier. The z-test here tells you how many SE away from the observed value is from the expected value, where the expected value is calculated using the no hypothesis. So Dr. No is now very intimidated by this number because negative 3 is very far away from the expected value. Negative being 3 SE away is very far away. In fact, the chance of that is actually 1 in 1,000. If the no hypothesis was correct, getting 48 or getting something that is 3 or more away is 1 in 1,000. So that means that Dr. No would say, okay, fine. If the average was 50, it's very unlikely to get something like this, and so he'll concede that the average was probably below 50. This chance, 1 in 1,000, is called the observed significance level, also called the p-value, and so the p-value is in this case 1 in 1,000. So why do we look to the area to the left? We got negative 0.3. Why do we look to the area to the left? Well, suppose that we did this test and we get different numbers. I say I want to pick 500 tickets. I get the average is 47.2. The SD was 14.1. Based on this, then we calculate the z-score again. 47.2 minus 50 divided by 0.63. Again, 0.63 is the standard error if you calculate it. You get negative 4.4. So I do this test and I get negative 4.4. This is even stronger evidence against the no. 4.4 SE below the average is even harder to get than 3 SE below the average. Now what if I do this test again and we get 46.9 and 37 as the SD, and we do this again, we get negative 1.9. Well, negative 1.9 is closer to being 50, so this will be weaker evidence. And so the idea here is that we want to pick the error to the left of negative 3 because we want to find samples which give even more extreme z values than the observed one, and stronger evidence against the no hypothesis. So the p-value, the observed significance level, is a chance of getting a test statistic as extreme as or even more extreme than the observed one. The chance is computed on the basis that the no hypothesis is right. The smaller this chance, the smaller the p-value, the stronger the evidence against the no hypothesis. Yeah, that's very important to understand. So again, here's a summary. If we expect the observed value, we expect it to be around the middle of 50, and we get something this far away, then that's strong evidence against the no. So this test statistic z depends on the data. That's why p is called the observed significance level. And so this is basically an argument by contradiction. We assume that the no hypothesis is correct, our data, though, if it's extreme, says that that's a contradiction, because so we want to reject the null hypothesis. We want to reject the null hypothesis. So again, we assume that the average was 50. We got something that was 1 in 1,000. So that says that if the null hypothesis is right, to get something like this is only 1 in 1,000. So that says that this is very unlikely, and so we reject the null hypothesis. Okay, so we have to be careful that we don't misinterpret this data. And so, it would be easier if we say that P would be the probability of the null being right. It would be much easier if we say that P would be the probability of the null hypothesis given the data. However, remember, P is computed using the null. And so that means that we have to be careful that we don't think that P is the probability of the null hypothesis given our data. So the null is a statement about the box. And the null hypothesis is, we're gonna no matter how often you make draws, the null hypothesis is either always right or always wrong, because the box doesn't change. So what the observed significance level tells us is the chance of getting evidence against the null hypothesis. So getting evidence as strong as, or even stronger than, if the null is right. So the p-value is the test of the test is the chance of getting a big test statistic, assuming that the null hypothesis is right. P is not the chance of the null hypothesis being right. So this test of significance is that complicated. You have to first set up a null hypothesis in terms of the box model for the data, and then you have to pick a test statistic to measure the difference between the data and what is expected on the null hypothesis. And we have to compute the p-value, the observed significance level. So this is called a one sample z-test, what we did in this lecture. This other test is also a sample, two sample z-test in chapter 27 of our textbook. There's also a t-test, chi-square test. There's a lot of different tests. And the point here is that all of these tests, no matter how you compute the statistic, the whole process is the same as what we just talked about. So where do we draw the line? What is considered too small? So a lot of people consider 5% to be where the boundary is. Anything less than that, we should reject the null hypothesis. So if P is less than 5%, the result is called statistically significant or significant. Sometimes people put the boundary at 1%. If P is less than 1%, then the result is highly significant. Even more evidence to reject the null hypothesis. So let's do another example. Let's say that we want to test. In fact, we have a researcher, Charles Tart, who is doing an experiment at UC Davis to demonstrate ESP. So the idea that some people might have extra sensory perception is ESP. So we use a machine, a random generator called Aquarius, that generate four targets, maybe 1, 2, 4 or something. And then we're gonna pick a person. The person's gonna make guesses. And if they have ESP, then they should be able to guess correctly more often than not. By pushing the button, the machine's going to keep track of how many times they do this and how many times they got it right. And so Charles Tart selected 15 people who thought that they have special ability, and everyone's going to do 500 guesses. And so that means a total of 7,500 guesses. And of these, they got 2,006 of them correct. So now, even if they were guessing, they should get about 25% right? And so that means they should the expected value of the number right they get is 1875. Now they got 2006. That means they got 131 more than what is expected. So the question is this due to chance or is it something else? So we have to set up a box model. We have to come up with a null hypothesis for the box model. So we're going to assume that this is random generator does work. It generates 4 targets and everything has a 1 in chance of being picked. So we're going to assume that there's no ESP. Everybody is just guessing. So that's the null hypothesis. That 1 in 4 chance of being right. And so basically, we have this box model for the null hypothesis that says that there's a box of 4 tickets, 1, 1, and 3, 0. 1 for being right, 3 for being wrong. And this experiment is like picking out 7,500 tickets from this box. And so that's the null hypothesis. And so we have this box of 0 and 1, 1 for being right, 1 and 0 for being wrong. And so here's the z test: observed minus expected divided by the SE. And so in this case, the observed value is 2006. The expected value is 1875. Okay, that's 25% of 7500. And then we have to find the SE for the number of correct guesses. So this is the SE for number, SE for sum that we talked about. Because we have a box model, we do know, we have an assumption about the box model. So because the box model is 1 ticket of 1, 3 ticket of 0, we can find the SD of the box using that shortcut formula. And we get that the SD of the box is 0.43. Remember, big minus small, root of fraction of big times fraction of small. That shortcut tells us that the SD of the box is 0.43. And so the formula for the SE is root of the number of draw, root of 7500, times the SD of the box. So the SE is 37. That's the SE, the standard error for the number of correct guesses. So that means that the 2006 is actually 3.5 SE above the expected value, because 131, right? That's the difference between the observed minus the difference between the observed and the expected. 131 divided by 37, that's 3.5 SE above the average. And so that's very unlikely. If you look at the Z table, find the area to the right of that area 3.5 or higher on the Z table is 2 in 10,000. So that means that the number of correct guesses, the surplus, is hard to dismiss as chance. If they were just guessing, it's very unlikely to get 2006 correct. And so does that mean that this is strong evidence for ESP? Well, we have to be careful, because there's other, we should definitely reject the null hypothesis, meaning that is not just due to chance, it's not just guessing. That's what we can conclude. We can reject the null hypothesis, that is not because of chance, it's definitely not guessing. There's something else going on there, but it's definitely not due to chance. But there's other possibility other than just ESP, right? For example, maybe the machine is not working, or maybe the machine is giving some subtle clues about the right answer. Maybe the machine is spitting out numbers that has a certain pattern, and people pick up that patterns. And so we definitely reject the null as guessing, but there's other reasonable explanation other than ESP. Okay, thanks for watching.